Hi, and welcome to this clip going through question 1 from the Cambridge Chemistry Challenge 2021 paper. This isn't an official mark scheme, and all past papers and mark schemes are available to download at www.c3L6.com. It might be worth having a copy of the paper with you so you can follow it as we go through it, and I have little screenshots of the mark scheme as we go through as well. So just first a little few words about how we handle a Cambridge Chemistry Challenge paper. It might be that you haven't done a Cambridge Chemistry Challenge paper before. This is the front cover of every single paper that is taken. It doesn't matter which year it is. Some of the questions will be challenging. Obviously there's a challenge in the name which suggests that. This is to be expected. So the idea is that you use your logic and problem solving skills rather than recall factual information. When you do calculations, make sure you include the steps just in case you get the wrong answer at the end. That's good general advice for any exam because often you get method marks for trying the correct steps along the way, even if the final answer isn't quite correct. Marks are given for significant figures and units where it says appropriate number of significant figures. It's the same idea as you'd have in a normal exam. You look at the least sensitive number of sig figs in the data that's provided in the question and use that as a guide. And finally, you use the periodic table that is provided with the paper, not values from a periodic table that might have come from with your exam board's past papers. So we'll show you the periodic table in a second. You can see that the values quoted for the relative atomic mass are to a greater number of decimal places, so they're slightly more accurate than the ones you get on general A-level data sheets. So looking at the first question, let's do part A. At the top you've got some contextual information that just starts the idea off. You don't have to worry too much about the fact that it's talking about space signs, but it talks about isothionates and the thiocyanate ion and gives some contextual astronomical connections there for you. So in the first part, it gives you some information. It's quite important to read that because then it starts talking about the chemistry. So it says when ammonia and carbon disulfide react, 2 moles of ammonia react with 1 of carbon disulfide to form a mole of an intermediate compound A. So to do the dot cross diagram for carbon disulfide, first of all, you put the carbon in the middle and the sulfurs on either side. And to deduce the dot cross diagram, you start by looking at how many electrons are in the outer shell. So this is GCSE knowledge. You could also use the periodic table, obviously, as a guide. So 6 electrons in the outer shell for sulfur, because it's in group 6, 4 electrons in the outer shell for carbon, because it's in group 4. So therefore, to complete the outer shells, you need, respectively, for sulfur 2 electrons and for the carbon 4 electrons. So that might suggest 2 double bonds. So if we put in the electrons for sulfur, 6 electrons per sulfur atom, and then little crosses for carbon, we can also think about the connection between this and carbon dioxide. So you may remember carbon dioxide from your textbook. It's very similar in the way that it's put together, as you can see, and it's a linear molecule, so therefore the bond angle would be 180 degrees. So if we look at the mark scheme, you can see that the structure that we've drawn would be the correct one with 180 degrees. So let's look at the next part. They want an overall equation for the reaction between ammonia and carbon disulfide. So the ammonium thiocyanate formula that we're looking for is NH4SCN. Obviously the cation is the NH4 and the anion is the SCN. So it tells you that 2 ammonias and carbon disulfide make an intermediate compound which goes on to decompose into NH4SCN and H2S. So bringing those two things together by cancelling out intermediate compound A gives you this. Now the molecular formula they want for part III, as any other molecular formula, it's simply a list of all the carbon, nitrogen, hydrogen, sulfur atoms. So taking into account the mole ratios, meaning 2 moles of NH3, you'd have CH6N2S2. And there you can see the mark scheme matches what we've done. So going down to the next part, part B, again some information is provided for you. So recall that a nucleophile is a species containing a lone pair which can be donated to form a dative covalent bond. It's obvious that the nitrogen in ammonia is going to have the lone pair here, so ammonia is behaving as a nucleophile. So you put 2 electrons towards the carbon because the carbon is delta plus and the sulfur is delta minus. Remembering when we construct curly R mechanisms, we need to put in dipoles as well. So therefore that means one of those bonds between carbon and sulfur must be broken, which gives us this structure at the bottom. Now that's one possible answer. It's not the only possible one, so you can see from the mark scheme there's other ways that you could construct a structure here. So then it says for part II, suggest a structure for the intermediate compound A. So recalling our molecular formula of the intermediate compound was CH6N2S2, and the structure is deprotonated by a second ammonia. That means that NH3 reacts with X to make NH4+. In doing so, removing a hydrogen from X to leave A. Okay, so this is our structure X. So this would be ammonia coming along, deprotonating by removing a hydrogen. That puts 2 electrons from that bond back onto the nitrogen, which gives us that structure at the bottom, which is CH6N2S2. And you can see from the top mark scheme that matches one of the options that we've got. So for part C, sulfur-carbon bond lengths in isothiocyanuric acid and in thiocyanic acid are quite different, as are the carbon-nitrogen bond lengths. So remember, when working out the structures here, just like drawing out organic structures, the number of bonds each atom has will guide you. So carbon must have 4 bonds, nitrogen must have 3, any N pluses must have 4, and any H must have 1. Sulfur will have 2 bonds. So isothiocyanuric acid is this structure here. Thiocyanic acid is this structure here, making sure that sulfur has 2 bonds, nitrogen has 3, hydrogen has 1, and carbon has 4. So let's think about the bond lengths. There's 2 things going on here. First of all, multiple bonds are going to be shorter than single bonds, so triple bonds will be even shorter than double bonds, because every time you do a multiple bond, you have overlapping pi bonds like in alkenes. So that draws the atoms closer together. There's also an electronegativity consideration. So let's say you've got a sulfur double bond carbon and a nitrogen double bond carbon. Nitrogen is more electronegative than sulfur, so it's going to tend to pull on those bond pairs more strongly than the sulfur will, so therefore to pull itself closer to the carbon than the sulfur might do. So if we label each of the bonds that the question talks about, okay, that gives us an idea here that we've got an increasing bond length going from CN-thio to CN-iso to SC-iso to SC-thio. So we take away all that text there, put in the mark scheme, that matches what we've drawn. They don't really worry too much about bond angles here because they weren't asking you that. And you can see that our increasing bond length trend is the same as theirs. So part D says ammonium thiocyanate has 2 nitrogen atoms in very different environments, one in the ammonium cation, the other in the thiocyanate anion. However, on warming, it isomerizes to form a covalent molecule, compound C, in which both nitrogen atoms are in an equivalent environment. So quite a lot of information to process there. So what you need to do is visualize the normal version of ammonium thiocyanate first, using the information that they give you. So that would be something like this. Then it tells you that a covalent molecule is formed, so there's no charges, no ions, and it's isomeric with the structure above, so it has the same molecular formula but a different structural formula. So you've got to have the same number of carbons, nitrogens, sulfurs, hydrogens, etc. So if we add up all of the carbons, hydrogens, nitrogens, and sulfurs, that gives us CH4N2S. That's our starting point, and from that we can build an idea of what possible structure to draw. When we're constructing it, remember, the carbon must have 4 bonds, nitrogen must have 3, sulfur has 2, and hydrogen has 1. That's our guiding principle all the way through. So that gives us something like this. And if you look at the mark scheme, that's exactly what they have as well. Then it moves on to the next part of the question. It's talking about mercury 2-thiocyanate. Prepared by mixing ammonium thiocyanate and mercury 2-nitrate became a popular chemical amusement in the 19th century. They compress into pellets, ignite the compound, smoulders with a blue flame, and gradually produces a large quantity of serpent polymer, which you can see in the picture. And eventually they realized that the toxicity of some of the products has led to a decrease in its use as an example of scientific entertainment experiment. Okay, so in the reaction, the compound decomposes to form three products: mercury 2-sulfide, carbon disulfide, and a polymer consisting of carbon and nitrogen only. So let's have a think about the information that we've got for part E, bearing in mind the information that talks about what the compound decomposes to. So part I, you'll notice, gets a little bit easier compared to what we had to do before. It only asks you to draw an equation for the complete combustion of 1 mole of carbon disulfide. This is a common strategy in the C3L6 papers in the way that they're designed. The questions get harder and harder and harder, and then they'll get easier again, and then the difficulty will build up. So from here, the difficulty will build up again, and then it'll go back to an easier question. It gives your brain a rest to allow your processing to sort of recover. Okay, so let's think about complete combustion. This is the idea that you get carbon dioxide from carbon, and from sulfur, obviously, you get sulfur dioxide, as opposed to monoxides or trioxides. So it's reasonable to assume that they want state symbols here, as we're dealing with relatively simple molecules, so you can guess that they're liquids or gases, like so. Now I've left a space there because obviously one carbon makes one carbon dioxide and two sulfurs make two sulfur dioxides. So the mole ratios for the product is quite easy. But then you need to look at how many oxygens you've got, or specifically how many O2s. So there's 6 oxygen atoms in total distributed between the products. So that must mean you have 3 O2s on the left-hand side. And that's what the mark scheme says as well, as you can see. Okay, the next part is a simple Hess's law calculation. You can see the data that they provide. So I'm going to use an enthalpy cycle to do this, drawing the reaction we've just put together across the top. That's obviously delta CH for standard combustion, because it's the combustion of 1 mole of your carbon disulfide. At the bottom, we put the elements from which those compounds are made, because the delta FH value for CS2 is provided. Now, as you go from the elements at the bottom to carbon dioxide and sulfur dioxide, that also means that you're combusting them, obviously, because it's oxides you're forming. We can now put in the data that the question provides, and that's our indirect route, and it's a dotted line. So, working our way around, that gives us minus 1077.9 kilojoules per mole. And if we check that against the mark scheme, you can see quite clearly that you've got it there. Now, why have they done 3 sig figs? That's because the minus 89.4 is the least sensitive there, and it's 3 sig figs. So that's what we call using an appropriate number of significant figures. So we change minus 1077.9 to minus 1080. Now the next part asks you to write a balanced equation for the decomposition of mercury 2-thiocyanate, giving the empirical formula of the polymer of carbon and nitrogen. Now we don't know what that polymer is yet, but we have been told what mercury thiocyanate is. If you can guess what it's going to be mercury in the +2 oxidation state because of the little 2 and Roman numerals, and therefore SCN minus is going to be used twice, hence SCN in the brackets with 2 next to it. Now the sulfide ion, similar to the oxide ion because they're both in group 6, is S2 minus, so therefore 1 mercury 2 plus goes with 1 sulfide 2 minus, so HGS 1 to 1 mole ratio. Carbon disulfide, we know what it is already, CS2, because the question has told us that. So with a little bit of deduction and playing around with numbers, we can get rid of 2 HGS and a CS2, and what we're left with is C3N4 as our empirical formula. And you can see that on the mark scheme as well. So in part F, there's quite a lot of new information that we need to think about. So they talk about something called thermal gravimetric analysis. This basically means slowly heating a small amount of material and monitoring the percentage mass drops as various gaseous products are released as the material breaks up or decomposes. So different decompositions will happen at different temperatures, and by measuring the mass loss at these temperatures, conclusions can be drawn about the composition of the original material. So in a small amount of the serpent ash, the stuff that's in the picture above, this is our C3N4, a mass loss of 78.5% occurred in the temperature range 245 to 370 degrees Celsius. This is less than expected, but this large mass loss can only be equated with the removal of one of the compounds from the serpent ash, although incompletely. So it means it equates roughly to one of the original compounds. So it might not be exactly the component we're looking for, but it'll be close enough. So if we just remind ourselves of the equation that we talked about, what we do next is we disregard the CS2, because obviously that's going to burn off as CO2 and SO2. If we look at the top of the sheet, you can see the blue flame produced from the combustion of the carbon disulfide. They put that into bold because it obviously has significance. So this is where you use that piece of information to disregard mathematically the CS2. So if we work out the MR of each compound, our mercury 2 sulfide is 232.65, again using the periodic table provided with the paper, not values that you might remember from your own periodic table. Your C3N4, as it stands, is going to be 92.07 grams per mole. So getting rid of the CS2, the serpent ash must be 2 lots of HGS and 1 lot of C3N4, which gives us 557.37 grams per mole. So to work out the percentage of mass loss, the MR of the decomposition product, whatever it happens to be, divided by the MR of the original serpent ash from which it came, times 100, should give you the value. So clearing some space at the top and putting that equation at the top again, doing it for HCS, 2 lots of 232.65, because there's 2 moles of it, divided by 557.37 and multiplying by 100 gives you 83.48. Doing the same for 1 mole of C3N4, 92.07, divided again by 557.37, multiply that by 100 and it gives you 16.52. So that must mean that if C3N4 represents the serpent ash left behind, the mercury sulfide must be lost in this temperature range too, because it also says at the very bottom on the left hand side, hence identify which compound is removed upon heating through this temperature range. Final bit, polymer of carbon and nitrogen that's formed in this demonstration is one of a family of carbon nitrides. So just having a quick look at that information at the top. There's quite a lot in there that you might want to use, so we'll come back to it as we go through the questions on this page. So part G, it asks you to draw the structure of the CN2 2- ion. So again, like we said, it's going back to fairly easy stuff. So CN2, 1 carbon in the middle, nitrogen either side. Remember, carbon has 4 bonds, nitrogen has 3. So let's put in carbon's electrons and then do the double bond. That's probably going to happen. So nitrogen has 5 electrons of its own. So let's put in some more crosses to represent that. Now, if you look at the number of electrons in the outer shell of nitrogen, there's only 7. So we need to put an 8th one in. So it complete this outer shell, hence the 2- in the question. So that must mean the structure will look something like that. And it'll be 180 degrees because it's a linear shape. Remembering that there's no lone pairs on the carbon in the middle, and the double bonds can be considered to be single areas of electron density or bonding regions. And there's our answer, which matches what we just came up with. Okay, so it then suggest 2 possible structures for cyanamide. So cyanamide in the question says that it's CH2N2, must include nitrogen having 3 bonds, carbon having 4, hydrogen having 1. I know I keep coming back to this, but these are the basic principles that allow you to work out these application type questions. So that's one way of doing it, and that's another way of doing it. So we're checking, does nitrogen have 3 bonds? Yes. Does carbon have 4? Yes. And does hydrogen have 1 in each case? Yes, it does. And those are the 2 that the mark scheme want as well. So then it says suggest a structure for melamine. So let's have a look at the information it tells you. tells you it's a trimer. There's 3 identical molecules joined together as one. So 3 lots of CH2, N2, that should say, sorry, can be used to construct this molecule. It's cyclic, and it's a 6-member ring consisting of C and N atoms. So for remembering the number of bonds each atom has, that gives us this structure here. Okay, that's our mark scheme, which matches what we've just come up with. So part H, a bit of application problem solving here. It's getting harder now. So 2 things to think about. The mass loss is very small as a proportion by the mass of the whole molecule, so therefore it's likely to be a small molecule containing 1 or more carbon, nitrogen, or hydrogen. So the MR of the trimer, 3 lots of CH2N2, is 126.38 grams per mole, using the periodic table values from the C3L6 periodic table. The dimer would be 2 melamine molecules joined together, so the dimer would be 252.76 grams per mole. So if to work out the percentage of 6.75, you can multiply that value by 0.0675, that gives you 17.0613 grams per mole. So the small molecule would be NH3. Now, in the dimerization, it says that NH3 is lost when the dimer forms. So you've got 2 molecules of your melamine there, and it's from here that an NH3 will be lost. So if we visualize that, that allows us to put that in instead as our dimer, nitrogen still having 3 bonds, hydrogen having 1, and carbon having 4. And that's our answer that we're asked to come up with. Now, you can see a little animation here. This animation is looking at the addition polymerization of E-butadiene. So there's 4 possible statements that explain why the elemental analysis of the graphite carbon nitrides, or GCN polymers, have a little bit of hydrogen in the formula. So where's that going to come from? So when the actual animation finishes looping, like it's about to do, you'll see that at the very end of the polymer chain, you're going to have a hydrogen atom. So the hydrogen atoms at the very end, or the very edges of the sheet, is what is going to be picked up by the elemental analysis. So they want that particular statement ticked on the answer booklet. Finally, let's review the structure of the dimer we're dealing with. It says calculate the empirical formula of the GCN that could ultimately be formed on heating melamine if all of the H atoms were lost in the form of molecule M from part H. So that's the structure of the dimer. The molecular formula is C6H9N11. If we lose all the hydrogen, that means all 9 hydrogen atoms are gone. That means we need to lose 3 ammonias, which means we take 3 nitrogens away from 11, which gives us C6N8 remaining. The empirical formula for that would be C3N4. They did it just using the melamine itself, so mathematically they just did it half of what we did it, but it ends still up as C3N4. Okay, I hope you found this useful as a quick run through of one possible way to do this question. Sorry about the couple of typos here. I thought I'd sorted them out, but obviously not. But even still, hopefully it's helped you have a think about this type of paper, and it might even inspire you to have a go at it yourself if you're considering doing it this summer. Okay, thanks a lot for listening. Until next time, see you soon.